fun.
It's but right now it's still like a little.
There you go.
Do I want to sign up for it?
All right, here we go, here we go, here we go. Magnetism. Jack was excited when he walked in. So it's Magnetism Day, it's the beginning. So we're going to start with a little brainstorm because I know that all of you in 3rd grade science talked about magnets. So you already are experts in some things magnet. So what I'd like you to do right now, I'm going to give you a minute, 1 minute, to write down as much as you know about magnets. Whatever, and this is not a conversation. This is you and your brain, your pencil, your paper. That's what I say to my young students. Okay. Why don't you combine with your table? Why don't you have a conversation at your table? See if you can make a list, a bigger, stronger list, and then we will compare big lists. All right. Let's start. Logan, do you want to start us off since you came in? I want to tell, hold on. Before I get too far, I want to make sure that I tell you, because we made a decision before you got here, that we are not going to do lab next week. We're going to switch that lab, and it's going to be on the 25th.
Like spring break lab? Wait, oh no.
After spring break. Yeah. No, we're not coming back. During spring break, show up. No, please no. Okay, what you got about magnets? Tell me something you know.
They have north and south poles.
They do have north and south poles.
Up top, Jay.
Why can't they be called east-west? You know?
I don't know. I don't know who decided this. All right, Brian, what else you got?
I got east. Wait, north, same repel and similar and different attract.
Okay, so like poles repel.
Dude, you messed up. I almost said east attract.
East attracts west.
That's just wrong. Like poles repel, unlike attract. What else, Gabe?
Magnetism is related to electricity.
It is. It is related to electricity.
Basically the same.
But is it the same thing?
No.
No. And this is one of those really tricky spots. They are very, very intimately related. We're going to fit them together really fast today, but you have to remember that they are different. Okay? Really?
Logan, what you back?
So, magnetism and electricity are related, but they are not the same thing. I have a lot of students, or I have had a lot of students in the past, that start to talk about poles as charges and charges as poles, and they are not the same thing. This statement is the same for both poles and charges, right? Like charges repel, unlike charges attract, same with poles, but they are not the same thing. Okay? And I really want to make sure that makes sense. You've got positive and negative charge, you've got north and south pole. Just making sure that's all there, because I don't want that to be a misconception. All right, what else you got? What else did you have written down?
If current comes out of the page, magnetic field goes counterclockwise. And if current goes into the page, it goes clockwise.
You had a really good 3rd grade teacher.
This isn't from 3rd grade.
What you think? I'm impressed.
Yes,
We'll get
follow.
there.
Yeah.
We'll get there. In fact,
We haven't started yet.
we're going to do that in about 2 minutes, and then you all will understand what he said. But I'm not going to put it on the everybody knows list. Is that okay?
Oh, okay.
Is that okay? No, I'm not saying you're wrong, but I'm not going to put it in the duh pile
We can
because
make a list nobody knows but AJ.
it's true. Or if you give me 2 minutes, then everybody will know. All right. Shh. We don't have lots of time. Go.
It creates a field. Magnet creates a field.
So there's such a thing called a magnetic field, right? So that's kind of like we've got the electric field that has to do with an electric force, and we've got a magnetic field. The magnetic field is marked with what letter?
B.
Right, because that's logical. But that's something that you do want to know, that magnetic field is marked with a B. It is a vector, which is where the little vector hat comes from. Yeah.
The more times you wind wire, the stronger the magnetic field around it.
Okay, so let's kind of extrapolate that a little bit, what kinds of magnets are there?
There's the ones that buzz when you throw them up in the air.
All magnets.
Okay, tell me more about what you're talking about.
Like, you know the little magnets that you take up and they throw them up in the air and then they hit together and they go.
Rare earth magnets.
Okay.
Fun
Yes.
magnets.
Okay, so let's talk more broadly here. Types of magnets.
Rocks.
I would say there are natural or permanent magnets.
Like a earth.
They're induced magnets.
Okay, so permanent magnets are things that are ferromagnetic and that have been magnetized by the Earth, right? Like there is a magnetic field in the Earth. You guys know that, right? Okay, so you've got the natural and permanent magnets. You've got the magnetic field of the Earth. So I guess you could talk about that as a type of magnet, not one that I could just go to the store and get. But I certainly could buy these natural rare earth types of magnets.
Is that because like the outer core is going around the inner core?
That's a theory. So we know that the Earth has a magnetic field. How do we know that the Earth has a magnetic field, by the way? And what is a compass?
It's a magnet.
A compass is just a little tiny magnet. And I got one over here I wanted to pull out to just kind of talk about. It's little, so I'm not going to like... You guys have all seen compasses before, right? So all it is, friends, is just a little tiny magnet that's put on a pin so that it is able to rotate, right? So, and we'll look at it with a permanent magnet in a minute, but basically that's all it is. So it's really nothing magical, right? We'll make that really clear. It's not magic. It's just a little magnet that's able to spin in whatever way it so chooses. So you've got compasses, and those compasses can indicate that there is a magnetic field of the Earth. In the Earth, okay, if we draw a picture of the Earth, sometimes they look at it, or people will draw it as though there is a bar magnet. To be very clear, there is not a bar magnet in the center of the Earth, okay?
If you dig deep enough, you can smack it. Just hit it.
Boom, it just, no. But, and this is the really important part.
See, it almost hits the.
Guys, listen. Thank you. People think, yeah, like, oh, well, duh, no, but we get that. But the thing that it's really important to know is that, like, geologists, geophysicists have been trying to figure out, there is not an answer right now as to what actually creates and maintains the magnetic field of the Earth, okay? Lots of planets have magnetic fields with varying strengths depending on things, but we don't really know what those things are. It's something that is still a current question. It's still open. We're pretty confident that there isn't a giant bar and that it has to do with the iron in the molten core, okay? And inside, you know, the inner workings of the Earth below the crust, but we don't really know exactly why or how. Okay? We do know that that the magnetic North Pole is not exactly aligned with the geographic North Pole. It's off by just a little bit. Okay? So if our geographic North Pole is up here and our geographic South Pole is here, the bar magnet, if you will, is tilted. Okay? And what pole is up here? The south. Yes. The south pole of the bar magnet is up by the north, what we call the North Pole, and down here we've got the north. Why is that? What's the deal there? Well, yeah, but that's not why this is.
Yeah.
The compass points north.
Because the compass, the north pole of the compass, points towards the south pole up here, right? So that's where the name comes from. That's why. Okay, so the north pole of your compass points up here because the north pole of your compass attracts the south pole of the Earth. Does that make sense? Okay, so that's kind of interesting and something, just, you know, piece of information. Another weird thing, and this is another thing that is really not well understood, but hopefully some good data is going to be taken pretty soon. The poles, the magnetic poles of the Earth shift. They flip every, I want to say it's like on the order of thousands of years. They don't know why. They don't know exactly how. The only thing that we know is that geologists have found that, doing excavations, you can see that there are alignments that are opposite what we would expect in materials down lower that would have been deposited thousands and thousands of years ago. Okay? So they know that the poles have shifted. They know that it happens every some number of thousands of years. They know that we're due. But we don't know when it's going to happen.
Doesn't the suns flip every 11
I think so. That sounds about right to me.
years? Every 11 years the sun.
I had a really lovely conversation with a couple of my extended family members a few years ago because there was a bunch of news about this. And my family members were freaking out, and they were like, oh my gosh, like what's going to happen when the poles flip? And I love them dearly, and I was like, friends, it will be okay. Like, it's not going to be a catastrophic issue. There are certain things that will be affected, okay? But it's not something that will cause us a lot of strife long term. Okay, but it's just kind of interesting. So you'll probably hear about it in the news, I don't know, sometime in the next 1,000 years. So, just keep your ears open for it. But it's kind of interesting. So anyway, there's the Earth. I'm done with talking about the Earth. What other kind of magnets do we have besides the Earth and natural permanent magnets? Induced magnets. So you can go get yourself a piece of iron. Is all iron magnetic?
No.
No, it's not inherently got two poles, okay? But you can align the little tiny magnets inside something called a ferromagnet. A ferromagnet is something that has some iron in it or some other very easily magnetized material, okay? And in doing so, you can induce a magnet. Once you induce a magnetic field or you align those little tiny magnets inside this material, it's going to stay aligned for some amount of time, okay? The magnets that you played with when you were in 3rd grade, okay, are not like rare earth metals, right? They were induced. And I actually have a device in the back that you can take these, because their magnetic field strength does vary and it does diminish with time, and you can actually re-induce that magnetic field very easily, okay, using a coil of wire and some current, okay? You can actually realign the little magnets, I guess I'll just say for now, to make it stronger again. So you have the natural permanent magnets, you have these ferromagnetic things. Are those the only kinds of magnets? Yeah, I hope not. Because a lot of things that we use magnets for, we want to be able to turn them on and off. Okay? If you've ever been to a junkyard or seen when they pick up cars and they move them around, they're using magnets, right? And if it was a permanent magnet, then you'd pick the car up and then you wouldn't be able to let it go. So if you use something called an electromagnet, okay, then you can very easily.
This big movie where it's like they pick the magnet up and they just shook all the people off.
Yeah, I mean, it just doesn't work, right? So,
Well, it works for people when they're trying to shake the people off.
I suppose. As long as, yeah. Because they're not magnetic. With an electromagnet, though, you can turn it on and off. And we're going to talk about that today. We're going to figure out how those work today, so that you kind of understand all of those pieces. I had one more thing written down about magnets that were important that you should know from your experiences, but I haven't heard yet. What's that? It does act over a distance. It's a spooky force, right? Yeah.
The inverse sword.
No. It's a very simple thing. Let me ask you this. I have a magnet here, right? It's got a north and south pole. Isn't it kind of fun? I hadn't noticed this until I started teaching this stuff, that N and S are both nice letters that look the same upside down and right side up. Maybe that's why they, I doubt it. But isn't that cool? Right?
Otherwise,
It's,
it's backwards
yeah.
E and M.
No, but it's like any letter when you like.
right? What's that?
Oh my
What's,
Oh my god.
all right, Teresa. Anyway, if I
It's Friday.
take, it doesn't work very well if you have to wait that long.
I didn't know he was doing it. I was
If I take this magnet and I cut it in half, then I've got a North Pole. Yay! All by itself?
No.
No. What would I have right over here?
Another South Pole.
Oh, and I have a South Pole over here all by itself?
No.
No, I have
Another North Pole.
a North Pole. So what is it that's interesting and different about magnets than about charges? One of those big fundamental things that's very different.
Every magnet divided.
You gotta get more.
They're reproducible, yes. No, what is it?
Every magnet must have two opposite, whatever it is, and all particles only have one charge. As far as I know.
Well, what are those things called?
Poles.
Poles, right? So you can have dipoles, right? A north and south, di means two. But can you have
A pole.
a single?
No.
No, it is not possible, according to all theories that we have right now, okay, to have a monopole. Monopoles do not exist, okay? You can't get one. You can't just cut and have just a North Pole and no South Pole. Now, if you've ever heard of string theory or done any reading about string theory or anything like that, so string theory is a kind of wild, crazy theory out there that is trying to unify all of physics, which would, be a nice thing to get things all to fit together nicely in a nice, neat package. There are some problems with it, including things like that we need 11 dimensions and some other issues with that. But one of the other things that the theory requires, this is all theoretical, not experimental, is that monopoles have to exist. Okay? So you have to be able to have magnetic monopoles in order for this theory to work.
Maybe someone will discover.
Wah, wah. So if you're a Big Bang Theory viewer,
Yes.
you know, like a bunch of seasons ago now, at the end of a season, beginning of another one, they went up to the Arctic Circle and they were trying to look for magnetic monopoles, right? Like that was his goal, because if they could find them, then sweet, right? Then he gets a Nobel Prize and da-da-da. But of course, wah, wah, it doesn't work. They almost kill him, but then they just fake the data, et cetera, et cetera. The key here is that magnetic monopoles do not exist as far as we know. Maybe that will change in our lifetime. If it does, great, but my guess is that it won't change prior to May. So based for the test that you're taking in May, you need to know that piece of information.
AP test.
I know, right? They're going to change. No, not so much. Okay. So questions there so far? All right.
Will string theory be on the AP test if it eventually becomes like?
Not in this class, because this is just mechanics and E&M, right? So maybe in physics 2, but not in this class. Yeah. All right.
Because you're all coming back next year, right?
So
Probably.
when we were talking about the magnetic field, this magnetic field can be created, we said, from a permanent magnet. We are pretty much done talking about permanent magnets now. Okay? Already, that was it. So I hope that you enjoyed that. Okay? We are now going to start talking about the relationship between electricity and magnetism. So I really like this story, and it seems very timely. So you guys may or may not remember that we had that Danish exchange, and I had forgotten until I was just looking over the book and taking some notes that this guy that we're going to talk about, Hans Christian Ørsted, was Danish, right? So I just sent a message to one of the teachers. I was like, "Yay, Danish people!" Right? Because it's super cool. And even cooler than that, this guy in 1918, Ørsted was his name, Oersted, The other thing that I like about this, he's sometimes known as the father of magnetism because he made a discovery that was a pretty big deal. He was just a high school physics teacher. Like, how cool is that, right? Like, yeah, go high school physics teachers, right? So he made this discovery kind of by accident, he was just monkeying with stuff and trying stuff out. And we're going to go look at what he did.
They never switched the wires back.
So, here's a picture of what we see, just to kind of keep in our heads and remind us of what is going on. So we've got no current. All of the compasses point in the direction of whatever magnetic field exists around. We turn on a current, and now there is some sort of magnetic field that is being created by that current carrying wire. Okay? What does it remind you of?
Oberke's like finger spinning thing that like baffles all the eighth graders, where if you have your finger and you spin it like clockwise above your head and you bring it down, it's all of a sudden counterclockwise.
Wow. We're going to talk about something that's related to that, but not that weird. Okay.
He's never told you that one?
All right, we gotta go. We don't have time.
So funny.
Here we go. Okay, so we need to talk about what's going on, how this works, all of this sort of thing. So here's the deal. We know, based on what Ørsted found out, well, what do we know?
Somehow electricity creates magnetism.
So somehow, let's start simple, and then we'll get a little more specific, right? So electricity somehow is creating, can I say a magnetic field? Is that okay, Brian?
Yeah.
Based on what you were saying. So, and we know that there's a magnetic field because we know that the compasses are being deflected, okay? So we know this.
Just how you get it.
Okay, guys, stop. Thank you. Okay, so in order to figure all of this out, we need to talk about directions of things, because if we're talking about a magnetic field, we know that's a vector, and we know that depending on which way the current was going, it's going to change the direction of that magnetic field, right? We saw that when we flipped over those wires and we drove all of the crazy, not crazy, that's judging. The people that are obsessed with color matches. Okay.
Rachel?
Well, yeah, it drove her nuts too, but there are a fair number of you in here. Okay, so from now until May, you need to make a commitment to me and to yourself for your sanity and your happiness in terms of your scores, that you will not break your right hand. Don't do it. If you're going to fall and like have some sort of something happen, left hand goes down first. Okay? Save the right hand.
Right hand.
Okay, what's that?
On the chest. Grab someone else's right hand.
I need your hand. Right? You have to have your right hand because the right hand tells you everything. There are things, yeah, and we talked a little bit, like we tiptoed into the right hand rule last semester, but we're going to it's going to be a big deal this time. So, no breaking your right hand. Got it? Let's practice. Put your left hand out. Catch yourself, right? Save your right hand, always, okay? So if we want to figure out the direction of the magnetic field, the direction of the magnetic field uses this thing we call the right hand rule. Okay? What's that?
What?
You're snarky and I'm tired. What are you saying?
Nothing. Never mind.
Okay.
I just felt like this is very discriminatory if you weren't born with the right hand.
It's true. Then you would have to make accommodations, which you'd probably have to do a lot of anyway. So there you go. All right. So here we go. Get your right hands out so we can take a look at this picture. You're going to put your thumb in the direction of the current. There it goes. And sometimes I find that it's easier to do this if I use my pencil as my wire so that I keep track of where it's going. Put my thumb in the direction of my current, and my hand, you're not going to hyperextend your hand, you're going to curve your hand in the direction that it naturally goes, and that will tell you the direction of the magnetic field. Got it? Boom. That's all it is. Okay? And if the current goes the other way, then the magnetic field goes the other way. Are you with me there? Now, are there any left-handed people in here?
I like the one in the book for imagining it too, though, where they say like if you're screwing it in, then like.
Yeah, that gets confusing though. I don't want to make it more complicated than you need to. Okay, so that's just me. If it works for you, great. So here's the thing: as a right-handed, you guys are all righties.
Sort of.
Are you ambidextrous? You right-handed. That's what I care about. So the thing you have to do when you're doing problems, you have to remember to set your pencil down and use your right hand. Don't try and use your left hand because it won't work. And don't tell me that you're going to try and remember it backwards because
It doesn't work.
I've had kids try and do it, and about half the time they get it wrong, and then I laugh at them. And I don't feel bad.
Oh,
Okay?
you laugh at me anyway.
Well, it's true, but I would laugh at you even more, AJ. Okay?
That's the worst things happen.
It's true. All right. A couple more things that we want to know. That B field is created at all points around a current carrying wire. Okay, so it's not just the places where we happen to have compasses. It's all around, and it propagates itself out as well. Okay, it is a vector with a strength that we're going to describe in just a second. Okay, and as we said before, that magnetic force is going to cause those compasses to align with it. So if we take this thing a little bit more literally and talk about the current, we know that a current is just a moving charged particle, right? So we've just got moving charged particles. And those moving charges are causing or are creating the magnetic field. The magnitude of the magnetic field is equal to, here it comes, mu naught over 4 pi, we'll talk about what that means in just a second, okay, times q v sine theta divided by r squared. That's the way that they first introduce it to you in the book, so that's the way I'm going to first talk about it, but we're going to
Avoiding the product rule.
parse things out really fast.
We're avoiding the cross product. So.
For about 5 seconds, and now we're not going to.
Right.
Okay? I don't know why they do in this book, why they say this and then they talk about it, and then they're like, oh, by the way, this is cross product. Because we've seen the cross product before, right? Didn't we play with the cross product a little bit last semester?
Even in this book.
Right, I know, like earlier in this book. So, here's the thing. We know that if you take two vectors, A cross B, what do you get? You get a vector, right? Yeah, the result is going to be some vector C, right? So we're going to find, we're taking two vectors and we're putting them together and getting another vector out, which is what we want here. What things are vectors here?
The B.
The B is a vector. That's good because that's the thing we want out. We need a couple things inside here that are also vectors.
Velocity is technically a vector.
The velocity is a vector, certainly.
Technically.
And R is a vector. The other things aren't because, we don't even know what mu is yet. Charge is certainly not a vector, my friend. So the way that we're going to write this...
Upward.
Stop. My gosh, if we don't get to everything today, it's not my fault. That's all I'm saying. I wouldn't even say that. Not put it all on Gabe. The mu naught over 4 pi is going to live right there. Q is not a vector. V is a vector. We're crossing V with the unit vector R because the R squared actually lives down in the bottom. Okay? So this is the vector version. This is the scalar version. And in order if you're playing with this one, to determine the direction, we're going to use the right-hand rule.
What was it?
Because it's in the denominator.
Wait, what are you asking? Yeah, that's just the directional vector. So it's got a value of 1, right? Does that make sense? Yeah. Yeah. Are we okay with that? Like that kind of process and transition there? Issues, questions? This relationship that they didn't really tell us where it came from, they just threw it at us, can be found experimentally by measuring the charge, the velocity, and how far away you are from whatever charged particle is that you're moving. Okay? So we can find this experimentally. It has a name, and its name is the it's 2 French names, so they have T's at the end, but you don't say them. Savart law. Okay? So they say in your book, I think it's kind of funny, it rhymes with Leo Bazaar. So bio-savar.
Never forget it now.
I know, right? So if you just...
Is it bio-savar or bio-savar?
I guess so, maybe it's bio. I've always learned bio, so I don't know. Either way, you don't pronounce the T's. That's the moral of the story. Okay? So, the bio-savar law is to magnetism what Coulomb's law is to electricity. Okay? It's kind of like one of those fundamental rules about finding quantities. Okay? Questions about that so far? We need to define a couple of things here, like mu naught. What is mu naught?
It's like epsilon naught, but for magnetism.
Yeah. Okay, we need one conversation, friends. Thanks. What is mu naught?
Permeativity.
Yeah, it's kind of like, what did you say?
Epsilon naught, but for magnets.
Right. So if you remember last units, we had epsilon naught, which was the permittivity, right? Permittivity of free space. And that was basically how easy is it to establish an electric field in a vacuum. Mu naught is the permeability of free space. Okay? And that is basically how easy is it to establish a magnetic field in a vacuum. Okay? That's what I was about to tell you. I'm glad you asked. This is where people get mad, so I'm just going to warn you not to get mad. There's a reason that we write it this way. Okay? Mu naught has a value of 4 pi times 10 to the negative 7.
What are the units?
Well, we got to figure that out, don't we? What? So why don't you da-da-da-da-da? Because we need mu naught. Mu naught is a special thing that we will learn about soon. It's beautiful and wonderful, and you got to keep it in its own glory.
We never really learned much about epsilon naught.
We will. It all fits together at the end.
Okay.
Poof.
So wait, so epsilon naught's gonna come back?
Oh yeah, at the very end.
Okay.
Yeah, like the last. The very end. It's like this big finale. All right. So, Jack wants to know what the units are. That's a really great question. Well, it looks like we probably need to figure something out with the units, don't we?
Well, what's B measured in?
Well, that's a good question. We need to figure that out too, don't
I
we?
like measured in
Teslas?
magnets.
B is not measured in magnets. It's named after one of my favorite physicists, the Serbian physicist Nikola Tesla.
Nay,
So B
measured in nickels.
has units of Tesla. If you've never heard about Nikola Tesla, he is a rock star. Brilliant, brilliant guy. He and Thomas Edison had feuds. You guys have heard of Thomas Edison, right? The inventor of the light bulb, right? No,
What
like
point of view?
they wrote wrote letters back and forth to one another that were like so, oh man, like it was ugly and funny. And Tesla was way smarter than Edison and kind of put him in his place a couple of times, but didn't have a lot of money to support what he was doing, and so a lot of what he did went unnoticed until after
He died.
he had died. Yeah, it's really sad.
It's like
But the reason that we have power the way we have it today is because of Nikola Tesla. So Thomas Edison was a big believer in direct current, and he was a big believer in basically every town and every city having their own power plant, having their own source of energy. And Tesla's like, that's not very efficient. That's a bad idea. And he was the one that really advocated for alternating current and being able to transport energy over long distances. So he is the one that we can thank for pretty much everything that we have now. Yeah.
What's the abbreviation for Tesla?
What is the abbreviation for Tesla? Big capital T. Yeah.
Didn't see it coming.
It is.
Why is alternating current better?
Because you have, in terms of transporting, you have much less of a loss than you do with direct current. We'll get there. We'll get there. Just hold on to that.
Keep your head up.
I promise. Probably, well, not until for a while, but we will get there.
Like after spring break.
April 1st.
Okay.
April Fools, we're not doing it.
Haha. Not going to tell you. 1 Tesla is equal to 1 Newton per amp meter. Okay.
1 Newton of force per amp of current flowing through the wire if you're 1 meter away from it.
More or less.
Oh my gosh.
More or less.
No sense.
Okay. Makes no sense or makes more sense? What'd you
No
say?
sense.
No sense, he says.
Makes more sense.
Also makes no dollars.
Oh, that's
Even
something.
worse.
Or nickels.
All right. We're not going to go through this right now because I got to keep going because I want to get through other things too. I'm going to tell you, so you're welcome, Jack. Pay attention here. That mu naught has units of Tesla meter per amp. And you can rewrite this with an actual number of 1.257 times 10 to the negative 6th Tesla meter per amp. Okay. So again, the reason that we have mu naught over 4 pi, even though mu naught is 4 pi times 10 to the negative 7th, is just something you're going to have to hold on to your hat about, okay? Go with it for now. It'll be okay, I promise. Fair? Okay. You'll see why it's lovely soon, but not yet. Let's see. So one other thing to pay attention to, and then we're going to try a couple problems to make sure that this part really makes sense. And that is that we have to, this is just kind of like a keep this in your brain thing. If you have a charge at rest, it has around it a what? An electric field, right? If you have a moving charge, does it have an electric field? It does. But now it also has a what? A magnetic field. They are not the same. They are related later. But I just want you to know that they both do exist. Okay? Okay, I want to do a couple of different examples here. I want to do some right-hand rule stuff real quick to make sure that this makes sense, this cross-product business. Let me put a space here so that we can do one at a time. These are examples from your book. One of them is example 32.2, and the other one is whatever they're called, like stop and think. 32.3. I don't know why there's one that's one and one that's the other, but that's just how they're labeled, so I just thought I'd let you know that. This first one says we have an electron that's moving to the right, so it's got some velocity this way, and the question asks, what is the direction of the electron's magnetic field at a point just below the electron? So at a point here, point P.
Does it matter that it's negative?
It does. It does. So we know, based on that equation, that B is equal to mu naught over 4 pi, blah, 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 but it's Q, and then we've got V cross R over R squared. So we need to cross the V and the R, okay? If it were positive, then we'd put our velocity vector in this direction. The first one, I can't remember, did we do this stuff last semester? I can't remember. The right-hand rule for cross product?
Yeah, a little bit.
A little bit? Okay, so here we go. Let's talk about it. So the first vector in this case, that's going to be the velocity vector, is going to be your index finger, okay? So remember that. It's going to be your index finger. And then the second vector is going to be the rest of your fingers. The result is going to point out of your thumb, okay? Okay? So if this were a positive charge, so first vector, I'm going to finish writing that. The second vector, so that's your finger, your pointer finger. The second vector, which is R, is going to be the rest of your fingers. And then the resultant will be your thumb. Because this is a negative charge, we actually are going to do negative velocity across the R. So the velocity is actually going to go this way.
Couldn't we have just reversed it and too?
You can too. Yeah, that works. I just don't. I get confused if I don't flip it right away, then I forget to flip it. That's just my deal. So that goes that way. The R is going which way?
Down.
Down. So which way is the magnetic field going? Out of the page.
Because the current's pointing in opposite direction, so V is negative.
Right.
Oh, okay.
Current goes that way. Yeah, yeah. So you can also do it with the other version of the right-hand rule and say the current's going this way, and so it's going to go into the page up here and out of the page underneath, if that makes more sense to you.
Oh.
Okay, so again, I think it helps if you put your pen in that direction. So if the electron is moving this way, the current's going this way, it's going into the page above, it's going out of the page below.
Current's going this way.
Current's going this way, R is down,
So it's going out of the page.
it's going out of the page.
And then it's
The magnetic field is going out of the page here at point P. And that's all they're asking in this
it's
question.
not like clockwise or counterclockwise.
No, it's just going to have one direction. Because the magnetic field is a vector, so it has a direction at that point.
Okay.
So if this were a current carrying wire, like if you were really looking at it as a wire, then you would say that it's going into the page up here and out down here. But you don't really need to say that in so many words.
So it's going straight out. Or,
Yes.
If you do a bunch of the field, right?
Yes.
That's right.
And how do we mark into and out of the page? Do we remember that? Did we talk about that?
Circles are out, X's are in.
X's are in, so the B field is going into the page up here. I don't remember if we've talked about this or not. And I just use dots. So the magnetic field would be going out of the page on the other side. Is that okay? Let's try this other one.
Would it change if we had like decided to classify electrons as positive?
Yeah, everything would be flipped.
So like the magnet, if you put a current through a wire and put this compass on it, they still point in the same direction.
I mean, what?
No,
Nothing.
It's just a label, right?
shouldn't change anything.
Yeah, nothing.
So physically nothing would change, but we would talk about the current going the other way.
Yeah.
Does that make sense? Do you want me to say that again?
Because your vector go into the face and out of.
No. The magnetic field we just would use a different mechanism to find out the answer.
Okay.
This setup over here doesn't care whether we talk about electrons or current or if we talk about anything. We could just talk about a box and a switch. And still those compasses are going to point in the same direction.
Yeah.
Right? It's just what we are talking about is current. It's all the human construct, right? This happened before we understood that there were electrons. Try this second one. That's labeled number 1. A positive charge is moving straight out of the page. What is the direction of the magnetic field to the right of the particle? So the particle is moving out of the page. We want to know what the magnetic field is somewhere over here.
Okay, yeah.
So again, you can do it one of 2 ways. You can say that the velocity is coming this way. The radius is going that way, so the B field is where?
Up.
Up. Or you can make you can use this one. It's the same rule. Coming out of the page and over here, it would be up. Are you okay with that? Anybody having issues with that? 'Cause if you are, we need to fix them now.
Can you just say that one more time?
Of course. You want me to do both of them?
No, just the last.
This one?
Yeah.
Yeah, so if your current is coming out of the page, then the magnetic field is going to go around in a circle. So up here it would be going this way, and over here it would be going this way, and this way. That's supposed to be a straight line, horizontally. And this would be going that way.
Okay.
Is that what you meant?
Yeah.
Okay.
I'm
Yeah.
just imagining the AP test right now if the proctors don't know anything about physics.
It's a
Just
wonderful,
watching
beautiful
us.
thing.
Just
Yep.
watch.
They think you're like making gang signs to each other. It's really, really fun. Yeah. The proctors always say something to me afterwards. I'm like, yeah, that's physics. Go team. Yep. So, yeah. All right. Let's try a problem. Oops, you can't see that.
Tie.
Ivy. Oh.
Yeah, that's what I got.
What?
Ivy.
A proton moves with a velocity that's fast, but not too fast, in the I-hat direction. I just didn't want to go through and find an I-hat thing this morning. As it passes the origin, what is the magnetic field at the following 3 positions? You can do it. Go, go, go. Go, go, go. Which way is the I-hat direction?
X.
X.
Wait. If velocity and radius.
Okay, so let's draw a picture, shall we?
Yes, please.
X, Y, well, you tell me what you want to be X. I don't care. Here, let's do it this way. Let's make this the X, this the Y, and the Z's coming out. Is that okay? Okay. So it's moving with a velocity in this direction. So there's my velocity.
Wait, Z can't come out. Z has to go in the right hand rule.
Oh, you're right. It has to go in. Sorry. My bad. Z is going into the page.
Wait, how do we know that?
Because it has to fit
yeah.
this. Yeah. Thank you. Yeah. So they want to know the magnetic field at a point right here. So that's going to be 1, 0, 0. That's going to be here, right? And a point 0, 1, 0. So that's going to be here. And then a point
Into the.
over here along the z-axis. Right, there's the z-axis.
No, 1, 1, 0.
1,
beyond
1, 1.
Oh, I'm sorry. I was getting excited about z's.
Like sleep?
Yeah.
Yeah.
I'm tired. I
You
went to
know
bed
it.
late, you know.
You don't really.
So there, and there. You don't even need to worry about the z-axis. You're right. Go.
Does this rule only work for if the first two vectors are perpendicular?
If you think about it, the less exciting version, QV sine theta. The sine theta is the angle between
Like
V and R.
if here's V and here's R, theta is this angle.
Right. Yes.
Changes the map. No, 1.6.
Wait, what was that?
1.60. No, its mass is 1.67 times 10 to the negative 27
On the
kilograms.
axis, it would be like that.
Yeah.
That's cool. That's zero there.
The angle between V and R.
Okay.
Sorry.
It was like a funky K, and I was like, oh.
Don't you know what I'm writing?
The dielectric constant between.
Yeah.
Electricity and magnetism all fit together. Come on.
Sorry.
No, they should have used the dielectric
So
constant.
it would be
So at the point 1, 0, 0, what is the angle between the velocity and the radius? And what's the sign of 0? So what is the magnetic field for this one? 0.
I'm good, I'm not crazy. I got that.
You're not crazy.
I like how you wrote B and said Z.
What?
When you said Z, as in like that's when you were gonna write zero, you wrote 0, and I wrote a B. Like, oh wait. I'm sorry.
Okay, whatever. Woo! All right. At the second one, is there going to be a magnetic field?
Yes.
Yes.
Yes. Can you find it?
Yeah.
Yeah. Have you done that already?
No.
Go, go, go.
Because no one really listens.
What do you want to know? Don't you know everything?
Wow, alright, let's take the AP test.
Okay.
I know everything. I'm all ready for this.
That's good.
No, I'm not saying everything about everything. I'm saying about everything about this problem. You know that mu naught is 4 pi times 10 to the negative 7th, so the 4 pi's are going to cancel, right?
Okay, thank you.
You know Q?
Yes.
You know V? You know R? You know the sign of 1? Or the sign of 90?
No, my battery. I got a battery.
Interesting.
Can't do this
I
one.
can't do problems anymore, so
Oh.
I gotta go to sleep
Well,
class early.
Don't complain to me when you don't understand them on the test then, friend.
I mean,
Yeah.
I just plug in numbers and route.
7.
Listen,
Oh, it is.
That's a nice calculator. There you go.
I would do a lot to solve this problem, but this might be pushing it.
Will you type an essay on the click keyword?
What?
Will you type an essay on the click keyword?
Okay, we gotta go, because we're running out of time. Ah!
No, those are just marking locations.
No. Yeah, those are just, yeah, sorry. Not trying to confuse you with notation.
Stars.
That's a good idea.
Idea.
Times 10 to the negative 19. 5.66 times 10 to the negative
Out of the page.
So, would you say 5.66
6 times 10 to the negative 14th.
units Tesla
Out of the page.
out as well? Because those vectors have to be mutually perpendicular, right? So we only care about the part that's perpendicular, so it's going to be the same direction.
Crazy.
Okay. Are we okay? Okay. I'm going to keep going. We'll get test back next time because I want to get this done. So, Is that okay with everybody? If it's not okay with you, I'm sorry. All right.
Let's not ruin my secrets.
What's that?
So we've talked about a magnetic field from a charged particle that's moving. We haven't really talked about it in terms of a current, but we can do that. It's really not hard because we know that a current carrying wire is just carrying charges. So instead of writing this Q times V thing, I'm going to write this as delta Q times V. We can write that little piece from this equation. We had that Q times V over there. I'm going to write it as delta Q because, well, for a reason that you'll see in just a second. What is velocity? That's a unit. What is velocity?
Velocity is
the
the
change
charge.
in displacement over time.
Right, like what is velocity? It's what?
dx dt.
dx dt. Yeah. So this is delta Q times, that's not a dot product times, but I guess you know that since don't have a vector there. Delta S or delta X over delta T, is that okay? Okay?
Current.
Right, and Q over T, if we look at just this, right there, that's just current. Charge per time. So we can write this instead as I delta S. So that is like the direction in which it's going, that little vector in which it's going that way. Okay? So now we can write the Biot-Savart law again, but in this case we'll say B is equal to mu naught over 4 pi. Instead of writing Q times V times the sine of theta, or Q times V cross R, we will write I S cross R hat over R squared. It's an R, it doesn't look like one though. Okay. This is the magnetic field, okay, from a short segment of a current carrying wire. If we want to look at a longer segment of a current carrying wire, we're just going to take a whole bunch of short segments and add them together. That sounds like the job for a little calculus to me.
How short is a short segment?
A short segment such that the rest of the wire is infinitely long. We're just talking about like a little piece and the magnetic field a certain distance away from it. A super short. This is just going to get us to the next place, is really what I'm saying. So that means we have to do this next problem. So here we go. I think it's right here. We have a long straight wire carrying a current I in the positive x direction. The question is to find a magnetic field at a point that is a distance d from the wire. So we're going to draw ourselves a picture. We're going to do this super fast, but not so fast that we get confused. But stay with me here for just a couple of moments. So here's my wire. It's going to go on in both directions a long way, but I'm just going to draw this piece of it. I've got current going this way. I'm going to draw an axis, just so I've got something to talk about. Okay? And I'm going to put a point P up here, a distance d away from the wire. Okay? And I want to know the magnetic field at the point P from all of the little bits of wire, one of which lives maybe right over here. Okay? It's got some little tiny width, delta x, and it's located at a point on this axis, x sub I. Is that okay? And we want to find what the magnetic field is at point P. Okay? If the current is moving to the right, we get our right hands out, does it make sense that the magnetic field is going to be coming out of the page up at point P? Are we okay there? Okay? So it's going to be coming out of the page, and all we care about then is the magnetic field in the z direction. So I'm going to say BI sub z is the only component needed. Okay. So if we look at the bias of our law, it says mu naught over 4 pi times I delta x sine theta over r squared. I'm going to go ahead and write it with the sine theta in there so that we can talk about what that theta is and what else is going on. So I've got some distance r here, okay? And the angle that I'm really talking about is the vector between the current, okay, and the radius, which is actually this angle theta there. I'm going to go one more step. Okay. So I think that I can write things in terms of x and d for r. Does it make sense to say that r squared is going to be equal to d squared plus x sub I squared? Okay. And what about this? If I've got the sine of theta, theta isn't super helpful, but this thing over here is what, 180 minus theta? How is the sine of theta compared to the sine of 180 minus theta?
They're the same.
They are.
Why don't we just say 180?
What's that?
Never mind.
Okay. And the sine of 180 minus theta also happens to be d over r or d over the square root of xi squared plus d squared. We're not going to quite get there today, but I do want to put one more little piece together. I'm going to take these two and I'm going to take this one. I'm going to put them together. Here they go. And we'll start here next time. I'm going to say b sub I in the z direction is equal to, that's going to be mu naught over 4 pi, because that's not going to change. And I'm going to write this as I times d. You check this over the weekend. Make sure you agree with it. X squared plus d squared to the 3/2 times delta x.
That looks an awful lot like electric field of range.
There are a lot of similarities, yes. We'll integrate next time. Have a wonderful weekend, guys.